groups are natural somehow deformations of Lie algebras in fact, or the universal enveloping algebras. And the big difference of it is that there appears a Q parameter, a parameter, and the whole structure depends on this parameter, in particular the co-multiplication, the co-product that tells you what the tensor product of two modules is, depends on that. And that leads to that the category of modules, for example, of weight modules of quantum groups, is always a nice monoidal category with a braiding, but this braiding is quite, it's non-degenerate. It's very far from being as symmetric as in the vector space, except if you take this Q parameter to be 1 or -1. And now one can ask, what is this good for? And this was your question here. And what is it good for? Now you want to do two things at once. First of all, you want to. It's always. It's always hard to write down long commutative diagrams, right? This is how you do computations, and how do you prove things in categories? Just drawing diagrams and staring at them and until you understand what commutes or what doesn't commute. And now in these braided tensor categories, you have a graphical calculus. This means you can simply represent many morphisms by diagrams, and then instead, if you want to understand whether morphisms coincide, you don't have to handle big diagrams, but you just look at your graphic, you do your graphical calculus. Now, how do you come up with this graphical calculus? This whole thing came up late 80s, beginning 90s. So, for example, Tuarev wrote a very nice book on that, and Von Jones, he understood that he found the Jones polynomial, which gives you nice knot invariance. So how do these things relate, and how do they come about? What you do is you think about a knot or a link in 3 dimensions, and now you want to visualize it. So what do? Is you take your knot or link, you take a sheet of paper, and you project it on it, right? You just stare on it, but you keep track on crossings, whether you have an over or an under crossing. You also give these knots and links an orientation, just meaning an arrow in a direction. And now you would like to associate a number to it, or we should better say a morphism. This means you think about it, a knot to be labeled by an object in your favorite category, or if it's a link, each component to be labeled by a corresponding object in your category. And then the corresponding graphical diagram, the corresponding ribbon graph that you get that represents a morphism in your category, you want this to be then your invariant of your knot. So this is how it came about. And Von Jones, he used the quantum group of SL2. Right? Of course, you do things with what you can do, and he got very nice invariants, so that they come exactly from coloring knots and links with representations of quantum SL2. And then because you have the Q in there braiding, morphisms depend on Q, on the Q parameter, you in fact get polynomials or better rational functions in Q as your invariants. Okay, very good. So this means, how do you think about morphisms graphically? So in general, you write an object A and B, and we know a morphism we take by an arrow. We just have to decide a direction. If we write the arrow from A to B, it's a morphism from A to B. And if we want to say there is a morphism, we just draw here a coupon and we label it by the name of the morphism. That's just the basic thing we do. And now we want to do we want to use special things for all the morphisms we introduce. We can, for example, draw a morphism from so how do you want to think about this morphism? We want to think about this, the evaluation. So here we already do something. We have here here's some strand labeled by A, and if it is pointing upwards, we think about it as labeled by A, and then if we go downwards, we think about it as being labeled by the dual. And so that means here that we think about this one as a morphism from so this means here this strand labeled by A but with arrow in the opposite direction, we think about as a morphism from A dual to something, this from A to something, but here it's going nowhere and nothing. We think about the identity. So this means we think about this as a morphism from A dual times A, we have here two strands, to nothing. It's our evaluation. Same thing with the co-evaluation, we just draw it the other way around. So here we go from nothing to A probably I want to draw the arrow here, A dual times A. A times A dual. And now, okay, these are very basic ones. In particular, you see if you compose an evaluation with a co-evaluation, you put them together, you just get a circle, right? And and more generally, if I compose an evaluation with a co-evaluation, and I put in between somewhere a coupon, a morphism, then I get the trace of the morphism. So this would be here. And of course, I don't want to draw this so clumsily, but this would be the diagram that illustrates the trace of the morphism F. I would then... Okay. Now, most importantly for us are, of course, braidings. So this would be our braiding from A times B to B times A. We can also use have the inverse of the braiding, right? That it would be the same type of diagram, just that we have here an undercrossing, while here we had an overcrossing, right? That's the difference, right? And here already you can see that this makes a sense. For example, we could have a link that has two components, one link that goes like this, the other one just a little bit above it, right? And then so this means they don't cross at all. So this but now depending on how do I project it on a plane, they either don't touch at all, or they are given by just two overcrossings, but one of them corresponding to a braiding times the other one to an inverse, and of course the braiding times it's composed with its inverse is just the identity. So that makes already sense here. Another thing that makes sense is, what did I say quite at the beginning of last lecture, is that the associator satisfies this coherence axiom, meaning that any morphism from A times B times C times D to A times B times C times D, or even many more objects with any two bracketings that's just composed out of associators, any two such morphisms need to coincide on the nose. So this means it's the associator is for these ribbon diagrams is not important. The diagram holds for any two choices of associators. Okay. Now, why? So this means you simply can play a game. You can choose your favorite knot and link. You can project it on a sheet of paper, and you can color it with your favorite modules and your favorite category, and you can associate numbers and morphisms to it. Yeah. Now, for us, this is meaningful because of quite simple such graphs. Namely, we are interested in two such ones which are quite simple. So the Hopf link is this one. So we here call the objects A, B, and the symbol for the Hopf link is SAB. And sometimes one likes to write here this Hopf link symbol, just because in particular in the VOA setting you also have these S's associated to modular transformations of characters. And then the other one you want is the other diagram you want to have is here the ribbon twist, called theta of A. So that's an endomorphism on A to A. What you do is here, if you think about it in terms of morphisms, what do you do here is, here you have the self-braiding of A with itself. That's a morphism from A times A to A times A. So this means I can use duality on one of the two factors. I can take the partial trace on the one of the two factors, which means you close it on one side, and then you get this morphism from A to A. It's the ribbon twist. Okay, good. Now I want to illustrate two things. So yesterday I have illustrated only in the example of the Heisenberg algebra of its Fock modules that the characters enjoy somehow a nice SL2Z action, right? That it's an infinite dimensional vector valued modular form, if you wish. And the other thing I illustrated is that there is a Verlinde formula, which simply means you take this S matrix, or in that case better S kernel, and you use it to define a product on the space of characters, and this product coincides with the fusion product, with the dimensions with the fusion rules of the Heisenberg, of Fock modules of the Heisenberg algebra that we had stated earlier. And now this all is so interesting because it's intimately connected to categories, to the categorical properties. And so in the categorical setting, this theorem is not hard to prove. So so if the category is nice, so if C is what is called a modular tensor category, so what is that? It is a semi-simple. Every object is a finite direct sum of simple object. It is a ribbon category. It is finite in the sense that it only has finitely many irreducibles. I write finitely many simple modules, I mean isomorphism classes of simple modules. And one more property, and one has the non-degeneracy property. That this Hopf link factorizes. It's just the Hopf link of A with the identity times the Hopf link of B with the identity. That this holds for all objects B if and only if A is equal to the identity, or better, a finite direct sum of the identity. If this non-degeneracy property holds, This non-degeneracy property is equivalent to many other non-degeneracy properties. One usually calls it, says that there is no non-trivial transparent object. Then the statement is there exists a categorical SL2Z action. So the group that yesterday acted on our space of characters acts also SL2Z action on our objects given by the Hopf-Link and the ribbon twist. There are some rescalings going on, and it's in fact a projective action. And what I mean by action on object means you take the vector space that has a basis, the simple objects of the category. And and this is the theorem. It turns out if you can drop the semi-simplicity condition, but you have to keep the finiteness condition. Then under a suitable non-degeneracy condition, which can again be phrased in terms of this having no non-trivial transparent objects, you still have an SL2Z action. That was, I think, first proven by Lyubashenko. But it's more complicated. Now, what I want to present now is how you use the graphical calculus to get Berlini's formula. And by Berlini's formula, I mean this formula for multiplicities of tensor products, more or less for free via the graphical calculus. So this is a very...
Make a comment.
Yes.
So this notion of modular tensor category is a little bit weaker than what's usually called modular tensor category by derived from some of the ultimate authority in this.
Yeah.
Just a comment.
What's the... thanks. It's somehow one constantly stumbles over the same thing, that so many things are having the same name, but some authors mean slightly different things. So now there's also an emergent tendency to call categories that are not semi-simple modular tensor categories. So one has to be very careful what is exactly meant by that. But often people now call them log modular tensor category because of logarithmic conformal field theory, which is maybe a good name. So anyway.
Excuse me?
Yes.
So, I mean, in the proof of this theorem, could we really write down explicitly the action in terms of S and theta?
Yes.
Okay.
Yeah. There's this book, Modular Tensor Categories and Modular Functors by Kirillov and Bakalov. It's available for free on Kirillov's homepage. And that proof is extremely clear there. It's a 2-3 page computation, and it is a good exercise to follow it. It is really, it is very clear, and it is, so if I gave a course on tensor categories, that would be 2 or 3 hours of that course. I think you learn a lot, and there's nothing mysterious going on. Good. Another thing that is very clear and even simpler, I mean not even, well, you see what you have to do is Berlini's formula in some sense. And the nice thing is, in what I'm presenting now, you also see that I don't have to use semi-simplicity anywhere, in fact. Or you see what happens if I drop that, how you have to verify, how you have to modify the formula. So, maybe this, since we commented on modular tensor categories, Berlini's formula is again also a word that is a little bit overused. So I here use this for an explicit formula for the dimension of these fusion coefficients, which you should think about as a dimension of spaces of conformal blocks on the sphere with three punctures. There are similar formulas for any genus and any number of punctures, and that is actually usually also denoted by Berlini's formula. So you could also think about this as a special case. Anyway, it's not really important. What I do define now is this what I call open Hopf-link. So the symbol, you can call it phi, but you can also just think about it as a rough drawing of an open Hopf-link. So what you do is you take this diagram here. So what you do is here you take A and B. You take once the and you braid them twice, and so that gives you a morphism from A times B to A times B. But now you don't close it completely, like in the Hopf-link, but you only close it on one of them, on A. You only take the partial trace. Right? So this in formulas, this would be the partial trace, the trace on the factor A of the double braiding. So this means of the you have a first one braiding and then composed with another one. And now this is a morphism from B times A to B times A, and so I can take just the trace on one factor, and it gives you this diagram. And of course, and now in particular, if I close it again, this means I take the trace over B of this partial trace, I get the closed Hopf-link immediately. So that means, okay. So why do I do this? Because I now want to do one computation. I take three objects, and I take the open Hopf-link. Corresponding here, I don't color it by just A, but by A times B. And but what is the tensor product of two modules? That is just, let me write it down. You take A times B. That's by the definition of the tensor product of A and B. It's just the strand corresponding to A on one, and then the strand corresponding to B. But now what do I have here? Braiding is a natural family of morphism. That means it commutes with any morphism. In particular, it commutes with the braiding here. And same here, this braiding here, it commutes also with this braiding here. So I can move the whole, this complete smaller open Hopf-link, I can move it through here. I could equivalently move it through here. So I get automatic that this is the same as the Hopf-link corresponding to A. And then composed with the Hopf-link, open Hopf-link corresponding to B. Now, so that means I get that this is the composition of the Hopf-link corresponding to A on C, composed with a Hopf-link corresponding to B on C. Now, what are these open Hopf-links? They are endomorphisms on the module C. And what does this statement tell us? We have a map from our tensor ring of our tensor category to the endomorphism ring of the object C, and this map is a morphism of ring because the image of A times B is the composition of the images, right? So this means, and you see how enormously quick this computation was, right? I, in fact, did the exercise and wrote down the corresponding commutative diagram, and it hardly fits on a LaTeX page. I mean, on a whole page via LaTeX, and you use a small font size that it fits, right? So it's anyway.
Excuse me.
Yes.
I have a question. Could you explain a bit for the second equality?
Yeah, this is the important thing. So we have let's the point is we have that. So what can we have here? Here we have a braiding from A B to BA, and now what can we do is we can, for example, apply here a morphism here, F from A to A prime, yeah.
Yes.
Or we could also imply can also write the diagram as this, AB, and we could write down the morphism here. So what would we do here? Here we would first take the braiding of A with B. That's then the tensor product of B with A, and then apply the morphism F. So we get the tensor product of B and A prime. And so that means this diagram is a morphism from A times B to B times A prime. Here, we take the tensor product of A and B, we apply the morphism F from A to A prime, and we apply the braiding. But here we apply the braiding of A prime with B, while here we take the braiding of A with B. So we take different braiding isomorphism. Naturality of the braiding means that these two things are equal. That's the statement of naturality.
Yes, yes.
But now think about it. This whole thing here is just a morphism from C to C, right? And so this means, and here I do a braiding between B and C, or here I moved it down. So here I do a braiding between B and C. So this coupon here, this here is the F in here, and I should have called it B and C and not B and A. And now I use this naturality property to move it through.
Yes.
So it's a very good question, because so the whole point is so here your question and my calculation here illustrate that the whole graphical calculus gives interesting results only because of the, I mean, it only makes sense because of the naturality of the morphisms. That means you have all these natural families, in particular, most importantly, the braiding. Right?
Thank you.
You're welcome. Okay. Now, let's go on. Let me try to keep the hop link. Now, let's specialize. Let's assume all three of them are simple. So in particular, the endomorphism ring on a simple module is a scalar. So this means it's one dimension, it's just multiplicities of the identity. So in particular, we can identify each open hop link here with a scalar. That's what I wanted to say. And so this means here this formula becomes all of a sudden just a relation between the scalar associated to A times B on the endomorphism ring of C is the product of the two here.
I didn't hear the stuff on scalars.
Okay, we restrict that C is simple, so that the endomorphism ring on C is one-dimensional. So. Good. So in particular, it follows that phi, the open hop link of A and C is just some scalar. Let's call it A with this label. And the same thing for the all others. So now let's compute this number. So let's see. What do we know? And by computing, I mean I want to relate it to the closed hop link. But what is the closed hop link? This is the trace over C of the open hop link. All right? But this one is, the trace is linear, so it's the scalar times the trace of the identity of C, and this is this deserves the name dimension, and usually but since the tensor identity has a trivial braiding with any object, you can also identify this with the hop link corresponding to A and the identity. I could equally well have called this just the dimension and not A, C, the dimension of the object C. Okay. So we see, well, as long as this is non-zero, so we just so let's also assume that in fact for all simple objects C, so because and now we see, this we get the conclusion here from this computation that this scalar by which the open hop link acts on C is just the closed hop link normalized by the dimension of C. And this is symmetric, so whether I write it like this or this is the same. Doesn't matter. Okay. Now with this computation, we can now write down this identity in terms of hop links of the closed ones, right? So let me now erase this here. So then it follows from the computation that we did here. Let's call this identity here star. That on the left-hand side, we have the hop link corresponding to right. And this equation I can clearly simplify a little bit. Like this. Okay. Now let's define fusion coefficients. We define the fusion coefficient or the fusion rule. So, and here let me also assume that the category C is semi-simple, so that every module is a direct sum of irreducibles. So then this here is good. So this means the NABD, they are non-negative integers, and they tell us the multiplicity with which D appears in the tensor product of A and B. Okay, now
Sorry, Thomas, in the sum, D is where? D object.
D is over the irreducible. So this is over the equivalence classes of irreducible objects. Okay.
So the direct sum is not necessarily finite, right? Is it a finite direct sum or not?
No, it's necessarily finite because we require that A times B is an object, and any object is a finite direct sum of irreducibles.
Ah, yes.
Yeah. I mean, really, I want to go to the Verlinde formula in this modular tensor category. So, but let's go step by step. And in fact, if you go over step by step, you really see what do I use in every step, so that you see how I could have been more general.
Talking about in every step, why did you ask A and B to be simple before?
Really only for the definition here of the fusion rule. I could have, so you're a good comment. So here I wanted C to be simple so that I can assign these numbers. And here in this definition, I want also A and B to be simple for the definition of the fusion rule.
I also don't understand why you care if A and B are simple.
Write a formula for NAV.
I want to, I mean,
Yeah, sure, but why do you care if A and B are simple?
I
Definition you wouldn't need to, I guess.
no, I also don't need it in the definition, but I want to have a formula for the fusion rules where A and B are simple, right? And of course, if in a semi-simple category, you know the tensor product of all simple objects, you know it of all objects. Tensor product is linear, so if you know it, right? So if you know it for all simples, you know it for all of them.
Couldn't it also happen that S1, C is not invertible if C is not simple?
I want to comment on all these things, absolutely. Let's first say how long is this lecture?
Just a couple of minutes.
Yeah, but let me simply go on. So at the moment we have this formula, but now the Hopf-link also distributes over direct sums. So this means, I mean, this is now here the Hopf-link of this maybe huge direct sum, and this one here, let me continue here with this one, is the same as the sum over D of our fusion coefficients. And now I can have here the corresponding Hopf-links. Yeah. And this now gives me, of course, a great identity, because now if the category is finite, then this Hopf-link gives me a matrix of size, the number of irreducible objects. And if this matrix is invertible, then I can, of course, multiply it with the inverse. So we assume that this matrix SDC, where this D and C go over the irreducibles, is invertible. So, and of course, here I first assume that the set of irreducible objects is finite. Then I can multiply this by the inverse of this, right? So I can multiply.
I missed this step. Why is that equality?
Right, so it's just I insert here for A times B the direct sum, and I now use linearity, right? So that the Hopf-link of and now I just use linearity, that the Hopf-link of one object with C plus another object with C is just the sum of the Hopf-links. So if this is invertible, I can multiply both of them by the inverses. And then I can everywhere do a summation over C. But here it doesn't matter really. And then, what do this here then just becomes just a delta d comma e. So this becomes a b e. And if you compare this with last lecture was exactly a formula. This thing here was called Verlinde fusion coefficient, and it was defined as something like this, just that the sum over all irreducible was replaced by the integral over all irreducibles, and the S was not defined via the Hopf-link, but it was defined via the modular transformation of characters. Okay. So I demonstrated under, of course, a bunch of assumptions on the category. These fusion rules can be computed using the Hopf-link, using this formula. Now you can ask, let me tell you a few things that fail and a few things that still hold in general. So up to here, everything is fine. Here, everything is also still fine if I assume C to be a simple object, because then, of course, the endomorphism ring is one-dimensional. What is a big problem is, what Jörn just pointed out, is this dimension can, and in fact, it can vanish quite often. So this is one problem. The dimension in the semi-simple setting, that this vanishing problem doesn't appear. Another thing that happens, which is not really a problem but more very interesting, is that of course.
Semi-simplicity imply non-vanishing of dimension?
So vanishing of dimension implies that the object is in an ideal of the category, and all I can say is that vanishing. So the objects whose dimension vanish. There's a notion of a negligible object. Negligible objects have, in particular, the property that their dimension vanishes, and this, in fact, any morphism involving this object will vanish, and negligible objects always form an ideal. What I wanted to say is, in the non-semi-simple case, it simply always appears that you have these negligible objects. In particular, the vanishing of dimensions is not a rarity, it's in fact a normal thing. Okay, let's maybe leave that at that, but and point out one other subtlety that happens here. Really, you're not interested in simple modules because you will have interesting indecomposable modules, but of course, indecomposable modules can have larger endomorphism rings than just one-dimensional ones. They can also have nilpotent morphisms, and then these endomorphism rings are larger. It means this we can't identify the Hopf-link just with the semi-simple part. With the idempotent, there are also nilpotents, and so here the whole argument as such here fails, but it can be, I mean, you can modify it to get still something interesting. Now, in particular, the largest indecomposable modules are the projective modules, and it turns out that these projective modules usually all have this property that the dimension vanishes. And but what is very interesting, it turns out that under certain niceness conditions that hold on all the VOA categories that we do know, you can define a modified trace that you only have on these negligible morphisms, and you can use this modified trace to define a modified dimension to give you modified Hopf-links that give you a modified Verlinde formula, and everything is somehow still quite nice. Of course, everything is more tricky and more complicated to formulate, but from the categorical side, there's a lot that still works. Okay, let me conclude with that for the morning session, and you either go to lunch or you can still ask me questions.